Hello, welcome back. Our next topic is linear programming. So, linear programming is a very well studied topic in optimization literature, and the theory and the applications of linear programming are very rich. So, let us start discussing about linear programming. You may recall that in one of our earlier lectures, we discussed about transportation problem. So, there are two factories which produce some commodity, and that is transported to the retail outlets. So, the factories are F1 and F2 and the retail outlets are R1, R2 and R3. Now, every plant has a capacity of producing some AI units of that particular commodity, and every retail outlet has a daily demand, and let us denote that demand by Bj corresponding to the outlet Rj. Now, let us assume that X11 units are transferred or transported from the factory 1 to the retail outlet 1, and let us denote by Cij the cost of shipping 1 unit of product from the factory I to the retail outlet j. So, the variables in this optimization problem are Xij, and the objective function is to minimize the cost involved in shipping the finished product from the factory to the retail outlet. So, the objective function is to minimize sigma Cij Xij, and that is not enough. We need to satisfy some constraint that the amount shipped from the factory I cannot exceed the capacity of that plant or factory, and the amount received by each of the outlets should be at least equal to the demand of that outlet. So, we need to satisfy the constraint that sigma Xij over all j's is less than or equal to Ai, and sigma Xij over all i's is greater than or equal to Bj. And moreover, the number of units that get shipped from the factory to the outlet are non-negative. So, we can write the program as minimize Cij Xij subject to the constraint that Xij sigma Xij less than or equal to Ai and sigma Xij greater than or equal to Bj, and Xij's are non-negative. Now, one good thing about this objective function is that it is linear in terms of the variables. Also, if we look at the constraints are also linear in terms of the variables, and further there are some extra constraints which are non-negative constraints. So, depending upon the problem, these constraints may or may not be there. Okay. So, when the objective function is linear in x, the constraints are also linear in terms of the variables, then such a program is called a linear program. So, transportation problem is a classic example of a linear programming problem. Let us look at another example which we use in our daily life. This is called the famous diet problem. The problem is that we want to find out the most economical diet that satisfies minimum nutritional requirements. So, let us look at the problem description in detail. Suppose that there are n food items available in the market, and the number of nutritional ingredients that we are supposed to consume is m. Now, there is a requirement that each person must consume at least Bj units of nutrient J per day. So, that requirement is suggested by the dietitian. Now, there is a cost associated with each of the food items, and let us denote that cost by Ci. So, the unit cost of food item I is nothing but Ci. Now, moreover, every food item contains some units of the nutrient. So, let us assume that each food item I contains AJI units of nutrient J, and let us assume that the number of units of food item I that we consume is Xi. So, given this data, our aim is to find out what is the most economical diet that satisfies the minimum nutritional requirement. So, minimum nutritional requirement is that we should consume at least Bj units of nutrient J. So, this condition needs to be satisfied, and at the same time we want to find out the most economical diet. So, if we consume Xi units of food item I and the corresponding cost of the unit cost of food item I is Ci, then what we are interested in is to minimize the cost. So, let us see more about this problem. Now, corresponding to the nutrient J, we need to satisfy the constraint that Aj1 x1 plus Aj2 x2 up to Ajn xn is greater than or equal to Bj, because we should consume at least Bj units of the nutrient J per day, and each food item contains, each unit food item I contains Aji units of nutrient J. So, if we consume x1 units of food item I, x2 units of x1 units of food item 1, x2 units of food item 2 and xn units of food item n, then we need to satisfy that for the jth nutrient this condition is satisfied, and that should be satisfied for all j going from 1 to m. So, this is the constraint that we need to satisfy. Now, that takes care of the minimum nutritional requirements, but we also have to find out what is the most economical diet. So, that means that the cost of food items that we buy should be minimized. So, the cost is equal to C1 x1 plus C2 x2 up to Cn xn if xi is the number of units of food item I consumed and Ci is the unit cost of food item I. So, the problem becomes minimize C1 x1 plus C2 x2 up to Cn xn subject to Aj1 x1 plus Aj2 x2 up to Ajn xn is greater than or equal to Bj for all j. So, this corresponds to the nutrient j, and this constraint needs to be satisfied for all nutrients that we need to consume, and there are non-negativity constraints on the variables x. So, you will see that the objective function is linear in terms of the variables x, the constraints are linear in terms of the variable x. So, this is another interesting example of a linear programming problem. Now, there exists many more examples of linear programming problems in our daily life. Now, let us try to write this linear programming problem in compact form. So, we are given a vector C containing n components C1 to Cn and the matrix A whose columns are A1 to An. So, each Ai in each Ai vector in each column is a m dimensional vector, and suppose let us assume that B is composed of B1 to Bm. So, this problem or this program can be written as minimize C transpose x subject to the constraint A x greater than or equal to b and x greater than or equal to 0, where A is a m by n matrix, C is a n dimensional vector and B is in m dimensional space. Now, this is called a linear programming problem. As you can see that the objective function is linear in x, the constraints are also linear in x, and there are some non-negativity constraints. As I mentioned earlier, in some applications this constraint may not be there. Now, let us make some assumptions which are very reasonable, that m is less than or equal to n. So, when we talk about these constraints, the number of constraints is less than or equal to the number of variables. This is a reasonable assumption, and we also assume that rank of the matrix A is m, which is less than or equal to n. Now, if there are more constraints than n, then there could be some redundant constraints, or the system of equations may not be consistent. It depends on how the constraints are represented. So, if the redundant constraints are there, they can be always reduced or eliminated, and finally, we have a situation where the rank of the matrix A is m and m is less than or equal to n. Now, another important point is that the linear constraints which are of the type A x greater than or equal to b, they can be of the form A x equal to b or A x less than or equal to b. So, we could have equality constraints or inequality constraints in a linear programming problem. Now, let us see more about the constraint set of a linear programming problem. The constraint set is also called the feasible set. Now, if we take inequality constraints of the type the set of all x such that A transpose x less than or equal to b, or set of all x such that A transpose x greater than or equal to b, that denotes a half space. So, if we have in two dimensional space a line, and this is the set of all x such that A transpose x equal to b. So, then the set A transpose x So, this half space is the set where A transpose x is greater than or equal to b. So, that includes this set as well as the hyperplane, and similarly the other part this will be the set of points x such that A transpose x less than or equal to b. So, this denotes another half space. So, both the half spaces contain the hyperplane, and as you can see that each of these half spaces is a convex set. So, inequality constraint of this variety denotes a half space. Now, if we have equality constraint of the type x such that A transpose x equal to b, we know that it is a hyperplane. So, it represents an affine space, and that also is a convex set. So, every constraint in a linear programming problem is represented by a convex set. Now, if we combine all the constraints together, that represents intersection of a collection of convex sets. and we already know that the intersection of an arbitrary collection of convex sets is a convex set. Moreover, we have sometimes the non-negativity constraint. Again, they can be written in the form of x greater than or equal to 0. So, this set again is a convex set. So, therefore, the constraint set of a linear programming problem is a convex set. Now, let us denote the set of the type Ax less than or equal to b and x greater than or equal to 0 as a polyhedral set. So, such sets are called polyhedral sets, which are obtained using the intersection of half spaces. Now, if we have a bounded polyhedral set, then that is also called polytope. So, we are going to denote a bounded polyhedral set by polytope. Now, let us look at the constraint set by taking some examples. Now, consider this constraint set in R2, the set of all x1, x2 such that x1 plus x2 is less than or equal to 2, x1 less than or equal to 1, and both x1 and x2 are non-negative. Now, here is a diagram which represents the constraint set which is given here. Now, let us look at the first constraint. So, first constraint says that x1 plus x2 is less than or equal to 2. So, in the x1 x2 space, let us first take the line x1 plus x2 equal to 2, and then what we want is, we want x1 x2 to be less such that x1 plus x2 less than or equal to 2. So, we are interested in this half space which is indicated by this arrow. So, the half space corresponding to this hyperplane which is indicated by this arrow is the region corresponding to the first constraint set, or first constraint equation or first constraint inequality. The second inequality, x1 less than or equal to 1. So, first let us take the line which is x1 equal to 1. So, this is the line x1 equal to 1, and we are interested in all those x1s such that x1 less than or equal to 1. So, that half space will again be denoted by this arrow. So, we are interested in the half space which is represented by this arrow corresponding to the line x1 plus x2 equal to 2, and this arrow corresponding to the line x1 equal to 1. Further, we have non-negativity constraints which are x1 non-negative and x2 non-negative. So, x1 non-negative means that all the points in the right side of the x2 equal to 0 axis, and x2 greater than or equal to 0 means all the points which are above x1 equal to 0 axis. So, if we take the intersection of the half spaces formed by these two lines and the first quadrant where x1 and x2 both are non-negative. So, we get the feasible region or feasible set which is shown by the shaded region. Now, you will see that this set is a convex set. Let us take another example. So, here is another constraint set formed by x1 x2 such that x1 is greater than or equal to 1 and x2 greater than or equal to 1. Now, note that there are no non-negativity constraints on x1 and x2, but as we will see from the example that those constraints would have been redundant. So, even if those constraints were there, they would have been redundant. So, let us look at the x1 x2 space. So, x1 greater than or equal to 1. So, this is the line which is x1 equal to 1, and we are interested in all those x1s which are greater than 1 or greater than or equal to 1. So, the half space is indicated by this arrow. Now, the other constraint x2 greater than or equal to 1. So, first we draw the line x1 equal to x2, and the half space that we are interested in is indicated by this arrow. So, if we take the intersection of these two half spaces, that is shown by the shaded region in this figure. Now, you will see that this constraint set or feasible set is unbounded. Further, you will also see that x1 and x2 both are non-negative in this case, but even though they were not part of our original constraint set, the constraint set in this case is such that x1 and x2 both are non-negative. So, this is an example of an unbounded feasible set. So, the feasible set, in the earlier case we saw that it is a convex set which is bounded. Here the feasible set is also a convex set, but it is unbounded. Now, there could be situations where feasible set can be a singleton set. For example, suppose the feasible set is an intersection of two affine sets, and the two affine sets in this case are x1 plus x2 equal to 2 and minus x1 plus x2 equal to 1. Now, the intersection of these two affine sets is a point. So, if we have a feasible set which is x1 plus x2 equal to 2 and minus x1 plus x2 equal to 1, the set of all x1 x2 which satisfy this is only the point A, and therefore, the feasible set can also be a singleton set. But for most of our discussion, we will not worry about these kinds of problems, because when the feasible set is a singleton, there is no need to worry about finding a solution to the problem, because since the feasible set is the singleton set, that itself is a solution to the given optimization problem. So, this case is not interesting. Similarly, there could be cases where feasible set can be empty. For example, if we consider a feasible set of the type x1 plus x2 greater than or equal to 2 and x1 plus x2 less than or equal to 1. So, x1 plus x2 greater than or equal to 2 is the region or the half space indicated by the arrow which corresponds to x1 plus x2 equal to x1 plus x2 greater than or equal to 2. So, this half space is the region that corresponds to x1 plus x2 greater than or equal to 2, and the other half space is the half space denoted by this arrow which indicates x1 plus x2 less than or equal to 1. Now, you will see that there is no intersection between these two half spaces, and therefore, the feasible set here is a null set. Okay. So, again in our discussion we will not worry about this case also, because then the problem, the given optimization problem cannot be solved as the feasible set is empty. So, we will be mostly interested in those cases where the feasible set is non-empty and non-singleton. It may be bounded or unbounded, but our main focus will be only on those cases. Okay. Now, let us look at some more definitions before seeing how to solve the linear programming problem. So, assume that x is a convex set and any point x of that convex set x is said to be an extreme point, which is sometimes also called a corner point or a vertex of x if that point x cannot be represented as a strict convex combination of two distinct points in x. So, if a point belonging to the given convex set x cannot be represented as a strict convex combination of two distinct points in x, then such a point is called an extreme point or a corner point or a vertex of x. So, we will illustrate this using some examples. Now, let us consider the same feasible set that we had seen earlier. Now, this feasible set is a convex set. Now, let us take a point A. Now, this point A cannot be represented as a convex combination of strict convex combination of any two distinct points in the set x. Same is true for the points B, C and D. But if you look at E, E can always be represented by convex combination of any two points in the set. So, what we need to do is that we need to draw a line segment whose endpoints are in the set x, and that line segment passes through the point E. So, this point E can be represented as a linear combination, convex combination of any two distinct points of the set x, and that is not true for the points A, B, C and D. And therefore, these 4 points form the vertices or corner points or extreme points of the feasible set, which is indicated here, while E is not an extreme point. So, A, B, C and D are extreme points and E is not an extreme point. Now, here is another example of unbounded feasible set, and you will see that the point A is the only extreme point of this set. There are no more extreme points as far as this set is concerned. There could be instances where the constraint set may not have an extreme point or a corner point. For example, so if our constraint set is so this constraint set does not have a extreme point, because if you take any 2 points in this constraint set, if you take any point in this constraint set, that can always be represented as a convex combination of other 2 points. For example, we can take a line segment, say let us call it as PQ. So, the point A can be written as a convex combination of PQ. So, if we consider a set like this, which is a convex set, and this is the feasible set that we are interested in. If we take a point in the interior of this set, let us call this point as A, we can always draw a line segment PQ which is in the set, in the given set, and which passes through A, so that A can be represented as a strict convex combination of PQ. On the other hand, if we take a point which is here, you will see that we cannot express this point as a convex combination of any 2 points of the set. So, this is a vertex or an extreme point. So, this has an extreme point A. Now, now let us see more about the geometry of the constraint set and how to get the geometric solution of a linear program in the next class. Thank you.